So this is the outline of the kids survey together with the 2DF. So the fat dots here are 2DF. This area has now all been covered by Sloan, so there's many thousands, tens of thousands, hundreds of thousands of redshifts in these patches, which means we really have a good idea of what the foreground structure looks like, and we can try to weigh the group samples or the cluster samples of the large-scale structure in those fields. We'll in total cover 9 bands, so the optical part will be UGRI, and then with Vista we will do ZYJHK. So it's a very large, very wide band, multi-band rather, photometric survey. And these are the numbers for the depths. This is the part done by Vista from Z to K, about 1.5 magnitudes deeper than the UKIT survey, which has been done on CFHT, on UKIT. And then with the VST we'll do UGRI down to roughly 25th magnitude. And because this is all done in service mode, you can pick the best seeing time to do the lensing band, and so in the 40% best part of the seeing distribution in Paranal, which corresponds to a free seeing of about 0.7 arc seconds, we will do our R-band observations, which will be used for the lensing. And then when the seeing is worse, or the moon is up, we will do the other bands in an attempt to make everything as homogeneous as possible, which is something you can do because of this service mode. So let's see how these surveys all fit together in a kind of parameter space of area covered, depth, and wavelength coverage. So this is more or less in order of time. So at the wide end side we had SDSS from U to Z and CFHTLS deep, same bands. And then CFHT also had a wide component, which is a bit less deep, but a bit wider. And so you find that everything naturally clusters in this punchline, as it's called, which represents a comparable amount of effort with a different trade-off between width and depth. So the Sloan got a coverage with UKIT to form the UKIT part in the infrared. Pan-STARRS 1 and KIDS are similar depth, but Pan-STARRS 1 is covering a much larger area. KIDS will have U-band coverage as well, will have infrared coverage as well. Then DES will cover a larger area to roughly the same depth again without U-band, but with some infrared. There's a large but shallower infrared part survey with Vista called VHS. And so slowly this whole parameter space is filling up. Pan-STARRS 4 will go even deeper. Sloan, LSST will go even deeper over a very large area. And in the end we hope to cover as much of the sky as possible with Euclid. When I wrote the slide first, there were many bands here. Every time I look at this, the number of bands here goes down. But there will probably be at least a few bands in the infrared and at least one band in the optical, if it overflows. And of course, one other important parameter in all these things is image quality. If you want to do weak lensing, getting the good image quality is crucial in order to be able to measure shapes accurately and go very deep. And so that's where some of these surveys differ, and in particular the things on the left-hand side of the screen here, and of course the space-based ones are the ones where they're really concentrating on trying to get a good image quality. So how are we looking at the technical requirements in KIDS? So in terms of measuring shears, of course the good image quality is important. So first of all, in service mode you can make sure that you're observing when the seeing is good. That helps. We've got all kinds of technical things to keep the seeing down. We also don't have a variability survey, which doesn't complicate the scheduling. It means we can really simply keep on doing the good seeing images without any time constraint and fill out the weak lensing survey that way. The design is such that the point spread function is very well behaved. Of course, we're still in the phase where we can talk about what the design is, and we don't have the delivered point spread function on Sky yet, but we think it should be very good. And of course, we're involved in all the things to develop algorithms. On the photometric side, we have the many bands from U all the way to K, so that should give the photometric redshifts very stable with very few catastrophic outliers. A lot of stuff happening to do the photometric calibration. In the end, we may not need much of it because we're overlapping both with Sloan and with Sudden SkyMapper, which will do much of the hard work already. We may simply be able to calibrate off those, but we'll certainly do the cross calibration. So I think that may help a lot because they also have much wider areas that they're observing simultaneously. And again, there's a bunch of algorithms. Now, a small history of the project. This should have been a sign. 2002, this was the first part of the VST that was shipped to Paranal. Primary mirror, this is how it arrived. So, and that was in 2002. And certainly in Catholic countries, they say that breaking a mirror is 7 years of bad luck. And 7 years are now over. So that's what I'm clinging to. So since then several other things have happened, but in any case the status at the moment is that the imager that we built has been ready for a few years now. It's on Paranal, so that we plugged it in and it still works, so that's good. The VST telescope itself has been long delayed. It's had a project with, someone should write a book about it at some point, but not yet. Let's first concentrate on getting the thing working. At the moment it's actually erected on Paranal. For a long time, if you looked into the dome, this is what you saw, a big gaping hole with something that a workman left behind. Now there's a real telescope in there. The last thing to happen was that the primary mirror cell, which supports the primary mirror, had a lot of technical difficulties in getting finished, and then when it was finally finished and in spec and beautiful, it was shipped to Paranal, and it went through shipping accidents number 2 and 3 on this project. It got wet on the way out with rainwater, so then in Paranal they opened it, tried to see if they could fix it. They couldn't, so they sent it back, and then it got wet with salt water. So then they really had to make it refurbish it properly. They've now done that, and it's back on Paranal, and it's actually installed on the telescope now. This happened earlier this month. The big box arrived at the VST dome. The mirror cell with all the actuators beautifully working in it was there. It was hoisted into the dome, and now it's sitting at the bottom of the telescope. So now the telescope is basically ready to receive the primary mirror for the first time, and then receive the wide field camera, which goes under here. So we're getting there finally. It's been a very long story. So this is just to show that there is a new primary mirror, which actually is in one piece. And so Omega Cam is the camera that we built for this project. It's very similar to Megacam in terms of its specs. One of the special things is that it has an image analysis system, which means we can try to keep an autofocus loop running on the telescope. And the idea is that you have the focal plane here in the middle, but there's also near the edge of the field one CCD mounted ahead of the focal plane and one CCD mounted behind the focal plane. And that means that you can actually measure the shape of the wavefront. So if everything is nicely in focus, then you should see a similar size defocused star on both of these CCDs, but when you're ahead or behind a focus, one of them gets bigger and the other one gets smaller. And so by looking at that difference, you can tell how to correct the focus. And so these are mounted off the side of the science array in the view. And in fact, you can do this to higher order as well. You also have information on astigmatism and spherical aberration and things like this. So we simultaneously, not too dissimilar from what Nick showed in his span stars talk, we simultaneously are able to fit for all these distortions and send signals to the telescope and the primary mirror and the secondary mirror how to correct for these. And so here's a simulation of how this is going to work. These are the two defocused CCDs on the side, and if in a simulation you put the whole telescope horribly out of spec with everything misconfigured, simply by using the information in the defocused images and supplying signals to how to reconfigure the primary and move the secondary, you can get very quickly in a few iterations into a beautifully in-spec focused telescope. So we hope this will work. Okay, so that's the kids project, and I'm sorry I spent more time on it than I probably should have done in a review talk of surveys in general. But I think many of the other projects are facing similar issues, not necessarily in terms of things breaking, but in terms of what you have to think about in order to make a survey that's got a good chance of delivering the science that we're after. So in the last couple of minutes, I would like to broaden this out and talk about completely different ideas that are also out there to use gravitational lensing, or weak lensing in particular, as a cosmology probe. One of them is to go to the radio. In the radio, it's possible to take very wide field images. The point spread functions that you have there are very different from the optical ones, unless you're in the regime where the ionosphere dominates, then you basically have a similar varying screen that you're looking through. But the point spread functions that you face in a typical radio difframeter are defined by the UV coverage. So actually know what your point spread function is simply by looking at where your telescopes are parked. That means that you're, by definition, in a diffraction limited regime always. The trouble is that the sources are barely resolved, so you cannot get the high resolution usually. And the density is quite low, particularly of things which are not so compact that you cannot measure their shapes. AGNs don't really help you here. And this will stay like that until SKA comes online. With SKA, I think you'll be able to get a very large sky coverage with very high fidelity imaging in one shot. So that, I think, will eventually revolutionize this whole field in quite a way. In particular, because you can combine it with 21 centimeter tomography. You have perfect redshifts for these galaxies for the price of the shape in the same code. There's clever ideas for using the shape noise in radio maps, and one of them, let me just discuss that briefly. There's a nice paper from a few years ago by Morales, which shows what you can do if you have the velocity field of the galaxy. So here